everybody, welcome again to our course. Now in this lecture, if we return to our model and SAFE, we say that we assume that all the stairs are, we assume them as opening to make the slab to take into consideration the opening of the stair. Okay, this is the first case. But we have the second case, we need to check the slab against the second case, because here and real these openings represent the stair, so we must include the weight, the self weight, the load of these stairs. Okay, so we can go to file, save as, new folder. We can now, we will show now what we will do to check the slab against this case. Now we need to delete all this opening, okay, by deleting them. So we include now, instead of the opening, the weight of the stair that we need. Okay, so here we have now instead of the opening 0 load, we have 5.5 and 2. And now and the opening, here the opening, it's not a stair, it's a normal opening, so we let them as you show. Okay, so now we can do run again, and we will check the slab now without opening. This is the second case. So now we will wait under the software terminate from the calculation. So now if the slab now are safe against punching shear, long-term and short-term deflection, this slab will be safe for all the cases that we'll have. After check the slab, we need to show the rebars, the reinforcement rebars, and then we need to design the beams. This is the principal beams here. We need to design this beam using, we need to calculate the maximum flexural moment of this beam. Okay, now we will show the short-term deflection is safe. We can go now to punching shear. We need to check. Okay, all the numbers are below 1. Now let's go to the long-term deflection, minus 23, and we will show now that when we delete the opening, okay, the slab will be more efficient against the deformation. Okay, now let's type what we conclude from this project. First of all, we can the thickness. When the first conclusion, we can say that when we increase the flexure, so when we increase the thickness of the slab will be more efficient against punching shear design, and the deformation, okay, decrease. Also, when we increase the compressive strength of material F prime C of the concrete, the deformation decrease. Okay, this is very important. Now, the presence of the opening decrease the efficiency of the slab against and the formation of the slab. Okay, this is general conclusions, okay, that we can conclude them from this project. Now we can go to show slab design. Okay, can go to apply. Okay, yes. Okay, all, we didn't have any addition reinforcement. So now we can say that we have the full design of the slab. Only we need to design the slab here. Okay, sorry, the beams. This is the main beams. This is simply supported beam. Okay, we need to calculate the load of this beam. We will show this work on the next lectures. Design of our drop beams. Okay, so if we go to SAFE and open our model, let's open this model without the opening because this is the maximum load. Okay, we will show this beam. We can show now our beams. Let's draw the dimension. Okay, from this point, for example, to this point, and from this point to this point approximately. Okay, we can show that this beam support this area from this point to this point 6.45, and from this point to this point 6.6. Okay, this is the beam. This beam support this area of the slab. In addition to the self weight of the beams, in addition to live load, and in addition to superimposed live load. So how you can calculate the MU, maximum moment, flexural moment? First of all, let's calculate the WU, because if we go to show to get as we know, this is simply supported, so MU equal WU times, okay, sorry, times L square over 8, okay, sorry, and WU equal 1.2 dead load plus 1.6 live load. Let's calculate first of all dead load. The self weight, first of all, we have this beam is 40 centimeters, so 0.4 times 0.8, okay, times the gamma of the concrete equal 25. This is 8 kilonewton per meter, okay, so we have 8. Now the superimposed or the self weight of the slab equal to 0.25, sorry, 25 the gamma times 1 meter times 0.42, okay, so equal to 10.5 plus, okay, plus 8, 18.5 the self weight that this beams support, in addition to the superimposed dead load, we have 6.6 times 6 plus 6 point approximate equal to 7 13. Okay, 13 times this area times 11, this we calculate this area times 5.5 kilonewton per meter, 13. Okay, we calculate this length plus this length times the area, uniform area, superimpose dead load, 5.5 times 13, so 71.5 plus 18.5, this is the dead load, times 1.2, 108. Okay, the live load equal to 13 times 2 times 1.6 plus, now this is the live load plus 108, so W equal 150. Okay, let's do this. We need to do, let's do some self weight of the beam equal to 0.4 40 centimeter times 0.8 50 centimeter times the gamma of concrete. Self weight of the slab that the beam scale equal to 1 meter, because we need it by 1 meter times 20 times the thickness 0.42, okay, times the gamma of concrete. Now this dead load, superimposed dead load, okay, carried by the beam equal to the length of the area 13, okay, plus times the 5.5, okay, equal etc. So we do the sum of these numbers and we multiply the result by 1.2. For the dead load, for the live load, we need the area, the length of the area times 2 kilonewton per meter square. Okay, here kilonewton per meter square. When we multiply by meter, we have kilonewton per meter. This number is kilonewton per meter. Okay, and here we get 26 kilonewton per meter. All the number here are kilonewton per meter. Okay, so here we have times and we multiply this by 1.6 and we get the full live load. Now WU equal the 1.2 dead load plus 1.6 live load. So we get WU. Now we have MU equal W equal 150 times L square equal 11 square over 8. Let's the result will be times 11 over 8. So we have this number 2268 kilonewton per meter. Okay, because here we have meter square and here we have kilonewton per meter, so we will get this number kilonewton per meter MU. Okay, so we do the design of this beam against this moment from this beams. The beams with 60-20, okay, with here from shrinkage for shrinkage with this stirrups, okay, for and here. So now we can show the final result of this slab. Okay, we can show the thickness 42. We have 14, each 15 centimeter, or we can use 16 bar. This is the main beam, this is the design, the beams. MU, we can show MU equal 2268. Okay, so as we show here, this is the full result of this project. We can now go and we can show now, if you want, here. Okay, the construction of this slab. This is the main beam. We can show this is the reinforcement rebar and two-way X and Y, top and bottom. Okay, can show this picture, the columns. Okay, the huge span. Okay, corner columns. Okay, the main direction, we can show here the top rebars connection. Okay, between top rebars and the mid span. The thickness, check the thickness of the slab. This is after casting, the thickness 42. Okay, this is the full slab. Now also we can show videos about this. Okay, this is the full project. Column above the slab. This is the walls. Okay. Important project. This is, we can show the thickness of the beams above the slab. Okay. Okay, this is before, and this is the beams, 12 meter. Okay, to the walls here, also here can show. So this is our project. This is the final result. Okay, a detail CAD. Okay, shop drawings. So thank you for listening.